This is 15.1, 15.2 notes. So let's get started. This is chapter 15 is about equilibrium, which is related to rate, chapter 14. So let's take a look at what the information we have here. Here we go. Up, one too far. Let's try it back. So the equilibrium constant. So first of all, let's talk about what we mean by forward reaction and reverse reaction. So we have a situation, let me just see. Okay, they don't have the picture on here. What you're looking at here, if you follow along with the book, is N2O4, dinitrogen tetroxide, and NO2, nitrogen dioxide. This one is clear as a gas, and this one is brown as a gas. NO2, I've actually seen that as a gas. It's very dangerous. But if we're going from just N2O4 over to NO2, then you would see a rate law. Now we understand what a rate law is, and the KF means for the forward reaction. Okay, so the rate law is rate equals K, the rate constant for the forward reaction, and then we have, notice that we have like N2O4, only the reactant there. So that's just considering the forward reaction. But what if some of the NO2 then reverts back to N2O4, which does actually happen. So what if it reverses? That's what the Kr means for the rate constant in reverse. So notice that I have these two here. I have rate equals Kr equals NO2, and then because this is an elementary step, I have the 2 there. That actually correlates directly to the 2 that's in front there because of the elementary step. And then when we put this together, notice that if I have the forward reaction and the reverse reaction at equilibrium, because equilibrium means not that the reaction stops, but it means the rate for the forward reaction and the rate for the reverse reaction are going at equal rates. So they're equal to each other. If that's what's happening, then I have this expression here where the forward equals the reverse, and then instead of rates, I use the expression. I just substitute in the expression, and then the concentration of the reactant, and then the expression, the rate constant, and then in this case here, it's also the reactant to the second power. So if I rewrite this, I get the forward reaction over the reverse reaction, and when I solve algebraically, notice I got a product here. That was in the first one was a product, right? And that's to the 2 because of my equation that looks like this. And there's a 2 there to balance that, so that's where that 2 comes from. And then I have, of course, the original reactant. So this is going to be like our basis then. So the big K for equilibrium means that when a reaction is in equilibrium where the forward rate equals the reverse rate, then I can write this expression. Okay, so K equals, the big K of equilibrium equals NO2 squared, the concentration of NO2 squared over N2O4. Okay, and that, then we show that, I think that's coming up the next one, we show that with a double arrow. This double arrow means that the rate can go in this direction and it can go in that direction. So both directions. So then take a look at this. I have A for the coefficient of the compound of A, and B is the coefficient of the compound of B, and so on for the products, exactly like the reactants. Notice that this is products over reactants, and you're going to see this over and over again. So products over reactants. Make sure for concentration that you have the coefficients then out as exponents. We couldn't do that for when we just were talking about the forward reaction rate, but now that we're talking about the forward and reverse reaction rate, we can actually use the coefficients now for the orders. So what are the equilibrium expressions for these equilibria? So what I would do then is I would take a look at this. Now this is good to know. What's good to know is that some things have concentrations and some things don't. So when I have a solid of solid tin here, that means that the concentration of this is 100% or 1. So it does not have to come, like it does not have to show up into the equilibrium, the expression. So also I have another solid here on this side. SnO2 is a solid, so I don't have to consider that also. So what am I left over for? I'm left over with gases and aqueous solutions that I can actually include. Okay, so if we're doing products over reactants, big K equals products over reactants, then what I would do for this one here, big K equals, and then the products are the concentration of CO2 squared over the concentration of CO squared. CO squared. And that's what it would look like. Or we could do Kp, and that's the pressure instead of, so that would be the pressure of CO2, and that would be squared, and then the pressure of CO, and that would also be squared. So either one of those works because it's a gas. If it's a gas, you could go with either one. Now I'm going to do the next one in green. Notice that we have two solids here, which means that you cannot include those in your equilibria because they have concentrations of 1. So that means that all I have then is just this one here in the products, which means there's nothing on the bottom because our one reactant is a solid and does not get considered. So this would be concentration of CO2 squared. Or I could do Kp, and that would be equals the pressure of CO2 squared. And that's it. All right, let's do the next one. The next one is this one down here. Notice I have a solid, so I can get rid of that. I have Cu with a +2. I have Cu, that's a solid, and then plus Zn2 plus. So big K. Now this one I can only do the concentration. I can't do the pressure because there are no gases here. So here I got K equals, I do reactants over, products over reactants. So I got the concentration of Zn with a +2 over the concentration of Cu with a +2, like that. And that's it. And we don't consider the other ones that have the solids. So pure solids, pure liquids do not show up in this. Gases and aqueous solutions do in the big K equation. Okay? So let's keep going, see what we got. The equilibrium constant. Because the pressure is proportional to the concentration for gases in a closed system, the equilibrium expression can also be solved as Kp. You saw me do this on the last set of problems. So let's keep going so we can see this. How do we get from Kc to Kp? Now remember, for the first one that we had before, it was K equaled, and I had the concentration of CO2, like this, squared, over the concentration of CO squared, like that. Or I could write it as Kp. Okay, so this one is always, if you just see a K, it is always Kc. If there is like the K for pressure, there would be a P with it. So K, big K equals Kc, okay, which equals this, and then Kp would be written separately, and that's the one that's written like this. Like that. Okay, so how do we get K and Kp to equal each other? In other words, what kind of equation do I have where I can get K to equal Kp, or the other way around? Because sometimes you might be given Kp and you need K, or sometimes you might be given K and need Kp. Okay, well here's the equation for that. Kp equals Kc times R, this is the gas constant. Almost always this gas constant is for atmospheres, which looks like that. The temperature, of course, is in Kelvin, okay? And the delta N here is the number of moles. This is moles of product minus moles of reactant, okay? Whatever that equals is what goes up here for delta N. Okay, we're going to do problems where we have to go from Kp to Kc and Kc to Kp. Okay, so I understand that there's some confusion about what moles of gaseous product is and moles of gaseous reactant are. but I will go through that specifically with the problems for 15A. So take a look at the equilibrium. Can we reach from either direction? I wish I would have put more stuff on here. Let's see if we can find some. There, take a look at this. So equilibrium. So if we start off with 0 product and 100% reactant, then you get an equilibrium that stops here. What if we started with much less reactant and a little bit of product? You would get the equilibrium then to end up coming up to the same thing. Like you would end up in equilibrium no matter what the starting concentrations are. So this is data from the last 2 trials from the table in the previous slide. So let me just go back to that. So you can see here the initial concentration of N2 and O2 was 0, 0, 0, and then for this one we started with a little bit of it. And then this one is initial concentration of NO2, which was actually the product before. Well, either way, take a look at what the K is for each one of these. Take a look at how close the K is for each one of those, no matter where you're starting off. Whether you're starting off with a certain amount of this one or you're starting off with a certain amount of this one. It doesn't make a difference. We end with equilibrium concentrations are very relatively close together. So let's keep going with this. So you can see here that experiment 3 and experiment 4, that they came together to the same equilibrium concentrations. That's important. Take a look at this one. Equilibrium can be reached from either direction. Here I have, it does not matter whether we start with N2 and H2. This is talking about the Haber process. The Haber process looks like this, and that would be H2, bonehead. Looks like this, and then we get NH3. I need a 2 there to get 2 N's, and I need a 3 here to get 6 H's on both sides. So this is the equation that we're starting with. Notice that we start with N's and H's. That means we're starting with the actual, here's N's and here's H's, and then this would be the product. But in this case here, we're starting with 0 product. That's what this graph is showing us. Notice here, though, that we're starting with NH3, which is what we would consider to be the product, and started with no reactant. That means the equilibrium then goes in the opposite direction. The reaction moves in the opposite direction to go back in this left-hand direction and actually produce H2 and N2. Notice they're being produced at exactly the same amount as they are in the first one when we started with the reactants and no product. Okay, notice it doesn't matter where we start, equilibrium comes out to be the same. Okay, equilibrium comes out to be the same. All right, we're going to get into what does the value or the magnitude of K mean, but that's 15.3. So this is, that's it. That's it for 15.1 and 15.2.